Hey everyone, welcome to the first EEA Tech Talk for this academic year. Please. Speaker for today is Professor Uday Khankhoje from our Electrical Engineering Department. A bit about Uday sir. He received his B.Tech in Electrical Engineering from IIT Bombay in 2005. He went on to do MS and Ph.D. in Electrical Engineering from Caltech, which he completed in 2010. He was a postdoctoral scholar at the famous Jet Propulsion Laboratory from 2011 to 2012 and at the University of Southern California from 2012 to 2013. Since 2021, he is an associate professor at our department, where he leads the numerical electromagnetics and optics (NEMO) research group, which focuses on solving electromagnetics inspired inverse problems. With that introduction, I'd like to give the stage to Professor Uday.
Right. Thank you. Okay. All right. Thanks for the introduction and welcome everyone for this first Tech Talk. Hopefully, we will have many more in the semester. By definition, these Tech Talks are supposed to be at a level that should be accessible to everyone in the department. Okay. And with that in mind, I also made this talk in that format. So as the flyer of the event says, in case you read it, all you need is your background should be, high school physics is pretty much all you need to understand most of the talk. Okay. So title is about the electromagnetics of 6G, and in general, this is electromagnetics of how phones work, where are we, what is the future, what are the technical challenges that lie ahead of us. That's what I want to illustrate. This is a very new area, so a lot of things are not even defined. So by the time you guys graduate, you will be, in positions where you will be driving standards, frequencies, designs from your research work. So in that sense, it's a futuristic technology, right? So let's jump right in. From your mobile phone network, what is it that you would really want? So, I've already answered the first question over here. What you would really want is good data rate for the simple reason that, you can do your gaming and Netflix from wherever, right? Basic, right? Anything else that we would like?
We need to be accessible regardless of where you are.
You want coverage wherever you are. It should not be that you go inside your hostel room and suddenly no one can reach you, right? So that's exactly the second requirement that we have, time lag. Okay. We want good coverage, whether we are in, inside a hostel, mall. Hopefully, bad coverage in the classroom is okay, right? So that's what we want. Now, how do we achieve this, right? Obviously, there is kind of a state of dissatisfaction with how things are. I don't know if you guys were born when 2G was there, but then 2G became 3G, became 4G, became 5G. What is really changing with all of these so-called standards? These are called standards. Something is changing which is allowing more data, right? So basic EE tells you that to increase the data rate, which is related to how much bandwidth is occupied by the mobile phone, by the base station, you need to increase the carrier frequency. This is one of the basic principles of communication systems. Higher the carrier frequency, I have more bandwidth. If I have more bandwidth, I can send more data. I can send HD video instead of SD video, things like that. Okay, so this is one of the requirements if I want more data rate, right? What about coverage? So let me just do it from here, right? Now coverage is actually related to something much, much more basic, which is how does a wave spread? And the wave spreading, how does it depend on carrier frequency? This is something that we will try to understand in the next few slides. Any guesses as to how this goes? Do you think coverage will get better as I go to higher frequencies? Some attenuation may happen more at higher frequencies. Okay, attenuation is one thing. Anything else?
Signal dies.
That is attenuation. Signal dying is attenuation. Any other concept?
Beam width reduces.
Beam width reduces. Okay. Okay, so I'll come to it in the next few slides. Okay. So this is a fundamental question. How does data rate and coverage? These are two things I want. Very basic. There's actually a third requirement which I'm not talking about here since we are not directly able to solve it, which is Doppler. We are not traveling that fast. We don't have to worry about Doppler. Power. I want a battery that lasts for more than 15 minutes. right? You give me a great phone with number 1 and number 2 TikTok, but the battery life is 15 minutes, is no good. So I want a good battery, but let's leave that for other part of WE. These are the two things that we need to solve, okay? So the first part I've already answered, which is about data rate and carrier frequency, right? It is as the carrier frequency goes up, bandwidth increases, and therefore the data rate increases. Now, this is something that we have already witnessed with the previous generations of phone technology, right? So when we had 3G, there were two carrier frequencies that were allotted. One was 900 megahertz, the other was 2.1 gigahertz. These frequency allocations will change from country to country, right? So you must have heard of your relatives when they're going to US, they first ask, oh, will my phone work there, right? Because the bands they have and the bands we have may not be the same. So that's where these bands come in. That is the carrier frequency. This does not tell you how much bandwidth is available. How much bandwidth is available is the second part of the specification. In the case of 3G, it was quite small, 25 megahertz. Okay. Now, 25 megahertz was good enough to send emails with big attachments. But on a 3G network, you could not do a video call. Forget it. Right. Then came in 4G. Right. So 4G LTE, as it was called, had a few more frequencies. Right. Not terribly higher than 3G. But what changed? The bandwidth increased 4 times. Now, as the bandwidth increased 4 times, I could do more. I could, of course, do video calls. I could, of course, do voice calls, but I could also start doing video calls, like WhatsApp video calls. In fact, most of us currently are running 4G, and we can do video calls when the network is decent, right? Few of us have 5G. I don't know if Airtel or major carriers have they deployed 5G in campus. I don't know, right? But what has changed is bandwidth. Carrier frequency, not so much. Then 5G came a few years ago with a fundamentally different kind of an idea. 5G came with two possible frequencies. The first frequency was 3.5 gigahertz. This is called the FR1, frequency 1. And the second is much, much higher, 26 gigahertz, right? And the standards were specified for both of these frequencies. The bandwidth for FR1 was about 400 megahertz. So it's already, this became 4 times, now this became 4 times. So that means that if I'm in a good network coverage area, I can really do a lot of HD, YouTube, Netflix, whatever, that is possible. Okay. The higher frequency, 26 gigahertz, has even higher bandwidth. 3 gigahertz of bandwidth is available at this higher frequency. Okay. Yeah.
How do you arrive at these?
How do you arrive at this? So maybe Krishna can say more about it. How you arrive at this is a lot of. It's actually less engineering and more negotiations between telecom companies, telecom regulatory authorities. They go back and forth. There are military frequencies that different militaries will use, and they'll say, oh no, my X-band radar works at 10 gigahertz. You don't dare transmit within so much of it, right? So it's a political, technological, economic tussle. Okay, finally something comes out of it. And there are economic things. For example, Nokia may have invested put a lot of investment in building a chipset for operating at 3.5 gigahertz. And Samsung comes and says, no, 4 gigahertz. So you can see there's money involved over here. So it's not a purely technical thing over here that's happening. Okay, it's above 20.
All the deployed ones are 100 megahertz for 4G.
Huh.
All the deployed ones are just 20.
Yeah, this is maximum. In practice, you would get less than this. In most cases, in practice, you get less than this. This is like ideal lab conditions. Okay. Good question. Any other? Because this is also something I used to wonder about, that why are they different from country to country? Who decides them? I'm none the wiser now, but I know that, okay, it's not purely science happening over here. There's nothing physically significant. You can see, for example, all of these frequencies except 26 gigahertz are roughly in the same range. And there is physics involved in this over here, because if you start increasing the frequency too much, what happens is the absorption by rain, fog, these things start to increase. So you don't obviously want to work over there. In the atmosphere, there are certain frequencies which get absorbed by molecular transitions. You want to avoid those, right? So there's some basic physics which tells you the range. After that is negotiation and economics. Okay. So coverage is something that we have not yet spoken. We spoke about data rate. Now let's talk about coverage, right? So here is a typical floor plan, right? There may be a base station somewhere here and you're sitting somewhere here. Now this is a typical scenario in your house, office or hostel room. From where you sit, even right now, if each one of us pulls out our phone, we don't have line of sight to the base station, yet we have network, right? And that is simply happening because waves are kind of bending through the windows. Windows are open, waves are bending and coming to us. This is not some very great exotic concept. Same thing happens with sound. I stand here and talk, someone's just outside can hear waves, audio waves bounce around this room and exit out. It's possible. Right? Same thing is happening with electromagnetic waves. But how much it happens depends on the frequency. Okay? It's not the same at all frequencies. So let's study this a little bit more. Okay? Now let's get just a little technical. We'll talk in terms of the wavelength. We can talk in terms of frequency or we can talk in terms of wavelength. They're simply related by speed of light. Right? We've known that since class 9. And here is an engineer's trick. When you ask anyone what is the speed of light, everyone says 3 into 10 to the power 8 meters per second. Right? That is the physics kind of answer to it. The more engineering way of writing the speed of light is 30 gigahertz centimeters. Are the units correct? Length by time. So dimensionally it's correct. So 30 gigahertz centimeters. How do I interpret it? If the carrier frequency is 1 centimeter, this product should be 30. So carrier frequency of 1 gigahertz means wavelength of 30 centimeters. Carrier frequency 30 gigahertz, wavelength 1 centimeter. You can very simply just go between this. So 5 gigahertz, 6 centimeters, right? So that's easy to convert, okay? So now this is what we're going to look at. So we have an antenna. This could be your base station and it's sending some waves that's going through. This could be a door, a window, some obstacle or an aperture or whatever you want to call it, right? Now we want to study how does this wave interact with this, right? From some very basic concepts, right? Now there are 3 basic regimes of physics which all of us should know about because we are using our phones every day. We should know this. The first is when this wavelength is much greater than the size of the aperture. Okay? Can anyone give a quick example of this? We use this also. I mean, we used to use it more. We don't use it so much. We're not going that far back. Telegraph is really far back, huh? FM radio, right? We all hear what is the frequency of FM radio roughly? Radio Mirchi is 94 something, right? So roughly 100 megahertz. 100 megahertz is how many gigahertz? 0.1 gigahertz. What should be the wavelength? 300 centimeters, 3 meters, right? So 3 meters is much bigger than a window opening, right? Why is it impractical? Because the antenna size is meters, right? The antenna size is roughly proportional to the wavelength. So if the wavelength is 3 meters, my antenna size is not going to be 3 millimeters. It's going to be comparable to 3 meters. So a base station may be able to emit at 3 meters because it's dedicated sitting somewhere there. But what about my phone? I cannot have a 3 meter antenna on my phone. So that is one thing. The other thing is the lower the frequency, the lower is the data that I can push through it. So that's why FM radio is good for listening to songs. But has anyone heard of FM radio for video? We have never heard of that. Simply because there isn't enough bandwidth. Okay. So this is useful to know, but not practical for mobile technology. The next obviously is when these two are comparable with each other. Okay. So the comparable, for example, you saw in the 2G, 3G, 4G, 5G frequencies were roughly a gigahertz. 1 gigahertz is 30 centimeters. Our door sizes, window sizes are in that range. 30 centimeters, 100 centimeters, 5 centimeters over there, right? So when we are in this is called the wave regime of electromagnetics. Light can easily bend around. So it can bend around obstacles without any problem. Okay. So this is the second regime. And this is why you get network in your room, right? Because a 1 gigahertz signal has no trouble in just simply bending around an obstacle. Okay. The third regime is the other end, where I have the wavelength is much smaller than the obstacle size. This is optics, right? The visible range of frequencies is what? Wavelength is 400 nanometers to 700 nanometers, right? Nanometers. Size of objects, centimeters. There is no comparison between this. So this laser pointer, for example, is red light. So here, the wave nature doesn't play a big role. We get the ray nature. Ray nature means it has to travel in a straight line. This laser pointer goes straight over here. There is no chance on earth that it will bend around and go outside the room. Here, I need line of sight, right? So this is why the laser pointer, of course, does not bend. So this is about coverage. The other point mentioned over here was about attenuation. So those of you who have done your basic electromagnetics course have heard of the concept of skin depth. Skin depth is how much does a wave penetrate into a conducting medium, right? So when we talk about penetration, right, at this frequency over here, the skin depth is reasonably high. So the wave can travel a long distance inside. So what does that mean? That if I have a wooden frame, like a wooden door, a 1 gigahertz wave can travel through it. It will get attenuated somewhat, but it will still make it through. Right? Skin depth, remember, was what? The distance after which mod E, the magnitude of the electric field, falls by 1 over E. So that's simple. So here the skin depth is high, so I can penetrate. On the other hand, here the skin depth is extremely low. A simple demonstration of the fact is we cannot look through people usually, right? So optical frequencies do not penetrate through people. That's because the skin depth is on the order of microns. After a few microns, the wave just dies. There's nothing left to come out. So that is here. So as I go to higher frequencies, what is the takeaway? Coverage is dropping. Attenuation is dropping. That means I need to place more base stations to cover for the to counter the coverage problem, and I need to put more power also, right? So this is like we are in the favorite regime of engineering. You cannot, there's no free lunch. If you win some, you lose some. So by going to higher frequencies, there is more data rate. However, coverage is more and more difficult, right? So this is what we have to work around. Okay. All right. This is what we want, right? So for data rate, as I mentioned, we want to go to higher frequencies. So what has been sort of proposed by people is that the FR1, the first frequency of 6G, is speculated to be in the 7 to 15 gigahertz range. No regulatory authority has nailed it down, but this is what speculation is, and a lot of telecom companies and universities like us, we are assuming that it's going to be in 7 to 15. So even in our research collaborations, we have one team targeting 8 gigahertz, one team targeting 13 gigahertz, right? So we're trying to do work at both. There's going to be a second frequency, which is called FR2, which is insanely high, 140 gigahertz or 270 gigahertz. And this is really very, very speculative right now. No one has fixed which frequency is going to be. But if you read papers carefully, you will find, for example, a collaboration between Samsung and a university in the US, where they have made a 140 gigahertz on-chip transceiver. Why would a company like Samsung do that? It's not, I mean, all of this stuff costs money. So there is some speculation that if they build a full system at 140, then with their financial clout, they will try to push for 140. Right? As I go to higher frequencies, the amount of bandwidth really increases. So they are imagining things like virtual reality and so on, which needs a lot of data rate. Right? There is some speculation of 270 gigahertz as well. So we don't know. So this is going to increase data rate. The second technology that people talk about, which again is worked on in our department, is something which is called full duplex. Now, full duplex is an interesting idea. If you look at your regular phone which you are carrying with you, it is half duplex. So the antenna is either transmitting or receiving at a given point in time. It's not doing both. To do both, you have to do some extra amount of engineering. If you can talk and listen at the same time, obviously I can have twice the data rate possible. Or the other thing that people do is reserve one band of frequencies for talking, one band of frequencies for listening. Again, you are wasting twice. If you could combine it in one, you are that much better off. So this is called full duplex. So people are trying to do full duplex in this FR1 range, right? So Professor Radhakrishna Ganti and Aniruddhan, I think they have a company or a patent or something to this effect for doing this, right? So, you know, we are well prepared in that area. Because I cannot talk and listen at the same time. If the antenna is transmitting, let us say, it cannot receive. Because, so there is a transmitter chain, there's a series of RF components, let's say a low noise amplifier, there's a capacitor, there's a whole bunch of things. So if I'm sending data over here, if I start getting data in the reverse direction, transmit power, imagine, is much higher, receive power is going to be much lower. So this difference in power levels can damage some components on the circuit. So that's why you separate it with isolators and things like that. Okay. So far we are talking about data. Question.
Why there should be so much difference between FR1 and FR2?
Because so it's a good question. Why should FR1 and FR2 be so far apart? Because they are serving different applications. FR1, you can imagine you with your mobile phone walking around the department is FR1 because you need coverage, you need the wave to be able to bend. But let us say I have 3 routers or base stations in the corridor. When they are talking to each other, they don't need coverage. They can be, they're part of fixed architecture. So if you can assure them line of sight, I can increase the frequency as much as I want. I don't want coverage there. So the back end of it is a much high, think of them as pipes. There are bigger pipes to bring data to you, and the final last mile is done at a lower frequency so that I can spread around and cover. Yeah, so this FR2 is a bit of a mystery to many of us also, that why is such a high frequency. Frankly, I think it will not take off. That's if I were to put money on it, that's what I would say. But I think the companies which have spent a few $1 million on it will disagree. So we'll see. We'll find out in the next 5 to 10 years what is going to happen over here. There may be some very specific use cases where it works. We don't know. Right? Satellite doesn't happen at such a high frequency. Satellite happens, I think, 8 to 15 gigahertz, right? At this very high frequency, the wave dies very quickly, and the satellite is at kilometers. Inter-satellite, yeah, maybe, who knows, right?
I had a question. So, if what sir said about FR1 here being pushing on FR2 of 5G, how can sir be better than 5G?
So FR2 of 5G has practically not been used. So although it's there as a spec, no one is actually using it. It was envisioned for places, very, very high density urban places. Okay. It was deployed in, I think, couple of places like downtown New York and Chicago, they deployed it. The funny thing is that after doing all the fancy 28 gigahertz and all, they found out that the phone's battery died in 3 hours. So it turned out to be not very efficient. So compared to your usual phone battery, which will last for 2 days. So even though FR2 was suggested, it's not really being used. 15 gigahertz is also pushing it. My suspicion is that we will settle close to 7.
So at the same rate we would like to send as well as receive data.
Of course.
For example, if there is a video call happening.
Yeah, it has to be at the same rate.
But so let's assume that frequencies are fairly close.
Yeah.
But there is a possibility that the information mix.
That doesn't really happen. Information mixing, that is taken care of at the level of protocol. So the protocol will say, supposing I'm doing 2 different frequencies for talking and listening, then it's happening simultaneously. And I have, in technical words, I will have a filter that will filter out in the listening channel, filter out the talking part and vice versa. So information can, and if I have the same bandwidth available for talking and listening, I can send the same amount of data, receive the same amount of data simultaneously. So this is easy to take care of in engineering and protocol level. Okay. There is one big military frequency sitting in the middle of 7 to 15, which is the radars that you'll see at your airports and all. So that's why I think, so most of the discussion, either 7 or 15, it's going to be easier to do 7, coverage will also be more. But that said, we know that Qualcomm has deployed a experimental base station at 13 gigahertz in San Diego. So, people want to try out all of these things because the environment behaves differently at different frequencies. So, you have to study these things. All right. So, this is second option to increase data rate. The third option is something that has not been done so far, at least in RF frequencies, which is something called orbital angular momentum. These are kind of exotic electromagnetic states which can carry more information. So, I will talk about this towards the end of the talk. Okay, you have all heard of polarization, TE polarization, TM polarization. Think of this as a generalization of this. I can send information on TE polarization and TM polarization. They are orthogonal to each other, so they don't couple. So I can send data independently. Now OAM generalizes that even more. That's the idea over here. So these are the solutions that are being thought of for increasing the data rate. What is the elephant in the room that we have not spoken about? Coverage, right? So there is only one solution currently existing for improving coverage, which is something called intelligent reflecting surfaces, okay? Or people call them reconfigurable intelligent surfaces, something like that, okay? So what is the idea over here? Because coverage is bad, I put kind of smart reflectors in various places which can redirect the electromagnetic energy. So that way I can get data rate and coverage using the second solution. So I'm going to talk now about this IRS, okay? It's based on one very simple philosophy that if you cannot go past an obstacle, go around it. That's the basic idea. So here is an illustration. Here is my base station, right? Here are my users. There happens to be an obstacle here. It could be a building, could be a tree or whatever, and I'm not able to get coverage over here. So I introduced this IRS over here, intelligent reflecting surface, which takes this EM energy and redirects it. That's the basic concept of a, if it were just a reflecting surface, then it's just, I could just put a mirror, right? An electromagnetic mirror, like a metal copper sheet I can put. So angle of incidence equal to angle of reflection. So this doesn't solve it for me because these users will be in motion. I may be walking and talking, right? So that is why the I in the IRS. Intelligent means I need some way to figure out where the users are going. So that's what makes it intelligent. So let's study this a little bit more. Okay. So what it does is, as I mentioned, it redirects EM energy. The reflection direction is not fixed. It should be adaptive. It should be responding to where the user is. And you can put it on buildings. For example, there are tall skyscrapers somewhere. You could put it on the sides of buildings so that no matter where the user goes, there is some network path available for coverage. Okay, this is one thing. I have even seen places for example, where there are disaster zones. People put this IRS on the bottom of drones, and that acts like a reflector. That's also possible. Okay. Now, what is it not? One very simple idea would be capture the energy and retransmit it. That's possible. The problem with that is, if you look at the information which I send from my mobile phone to base station or vice versa, if you look at the packet now, it's a complicated thing. There is some header, then there is some data, then there is some guard band. It's a fairly complicated thing. So I would have to decode that and then retransmit it. Basically, the cost and complexity will go up. So I want to do this retransmission or redirection of energy without having to decode the waveform. Okay, so that is cheaper, and I can deploy not one and two but hundreds of them. If I wanted to do just one or two times, I can do a relay, but I want to deploy this at a low cost all over. Then it had better be cheap. And cheap, I mean, just a funny example in our department, couple of bathroom taps were stolen. So if I put an expensive relay, I mean, someone will just walk off with it, right? So we want it to be cheap because we're going to be mass deploying it, right? All right. Now let's go back to some very basic high school physics. How is it possible to change where a wave goes without mechanically moving the surface? That's what we want. Mechanically, of course, it's easy. Yeah, but I don't want an operator sitting on each reflecting surface. So how do we do it? So some simple ray physics over here. You have, let's think of this as a mirror. And I'm showing you two paths. One is from A to R. The other is from P to C. Right? Sorry, A, B, C and P, Q, R. Yeah, sorry. Right? And what are these dotted green lines? They are called the wave fronts or the normals to the direction of propagation, and they are the locus of equal phase. Right? The phase is equal on this, and the direction of propagation is perpendicular to that wave front. We all know this really from high school. So the path length from A, B to C is the same as the path length from P to Q to R. Right? This is simple angle of incidence geometry, you can figure it out. Right? Now if I break this up from here till the point of reflection, you can notice that A to B is a little shorter than P to Q. right? How much shorter? T times cosine theta. So the wave from A reached earlier, this guy reached later, but on the reflection to the final destination, this guy had to travel longer. How much longer? Exactly the same distance, T cosine theta, right? So this is how regular passive reflection works. We all know that. Now, what did we assume in deriving this? This is very important. The first thing we assumed is that the reflected field over here is just some number, the reflection coefficient multiplied by the incident field. That's how I get the reflected field. So if the reflection coefficient is say 90%, then 0.9 multiplied by incident wave is what happens. But the reflection coefficient can actually be complex. If it is complex, what is it doing to the incident field? It's adding a phase or subtracting a phase, right? So that is our clue, that if I can play around with the phase, what could I do? I can change this locus of constant phase, right? So let's take a let's look at the reflection at B and Q a little bit more carefully, okay? So let's do a thought experiment. So the thought experiment says that the reflection, so we know that when a wave travels a distance of one wavelength, how much phase does it acquire? 2 pi, right? So how much phase a wave acquires depends on how much distance it travels. That is clear. Now let us say some magic at the point Q, I put some kind of a device which injects an extra phase only at point Q. I imagine there is some technology that can do that. Now the wave, the orange wave which is hitting Q now has got some extra phase, right? So because of this extra phase, C and R are no longer on the same wavefront because the guy from Q has now been given some extra phase, right? So what can we do now? If I go along this line C just a little bit more, if I travel some distance, I'm going to get some phase. How much phase am I going to get, right? If I travel a distance T, I get a phase 2 pi by lambda times T, proportional to how much distance I went, right? So instead of C, there's going to be a point C prime, where now the phases have matched up. So C dash and R, that is now my new phase front. And if I draw a black line perpendicular to it, that's actually the direction in which my wave is going, right? So without mechanically moving anything, if I can inject a few phases here and there, what's going to happen? I can change the direction. No mechanical stuff involved, okay? So in this explanation, I simply just took 2 points B and Q. You can imagine doing this over a large surface as well. The concept is going to be the same. I need to control how much phase I add at each point so that I can move the beam wherever I want, right? That's the basic idea. Question? Huh?
Yeah, the amount of phase we need to add again depends upon
Where the transmitter is.
where the receiver, that particular person.
Correct. So I need to know where the transmitter is. I need to know where the user is. Corresponding to where the user is, I will back calculate what is my new direction, how much extra phase I need to add, all of that.
How do you weigh that?
How do you, or rather, how do you know where the user is? Yes, I'll come to that. I'll come to that. It's not a very simple system.
Inject the phase only if you know the operating frequency.
Everything is known. I'm designing the system. So I know, for example, FR1 is 7.8 gigahertz. It's in my hand. I designed it, so I know all of that. Right? This is that's the difference between this is engineering. We are designing it specifically so as to give us coverage. So I better know everything. Okay. Now the same concept that by changing phases I can move beams is also used in antenna arrays. Antenna arrays are those things which sit at the nose cones of fighter aircraft and so on, so that electronically they can sweep their radar beams. So that concept is exactly the same over here. So imagine I have 4 antennas. They all have the same current. The electric field from an antenna is proportional to the current. So if I have the same current in all, then all the fields are going to go up in phase. I'm going to get a massive beam at the top because they are all adding constructively, right? Now, supposing I want to tilt this beam, right? That's my fighter aircraft looked in the nose, now it wants to look over there. How will I do it? So again, notice over here, what is different between these paths? It's a bit of path length is different, right? So if I wanted to have constructive interference at this point, or rather this direction, I need to compensate for these differences in path length, just like what we did in the reflection case. So you can see that by geometry, if this distance is t, there's t cosine theta, and so on. Every subsequent antenna has a deficiency of t cosine theta in the path length. Therefore, phase is 2 pi by lambda into that. So I simply change the currents to be proportional to this phase difference, and now my beam goes in this direction. Standard technology used everywhere in what are called phased array antennas. You will see them in aircrafts, airports, and now in 5G also in some cases you will see it over here, right? This is called progressive phase shifting. Yeah.
That's a complex number.
This is a complex number.
Proportional to eigenvalues.
I mean, there are some constants over here which will depend on the antenna dimensions and so on. Those are constants. But
You're changing the phase of the current field.
I'm changing the phase of the current.
Phase of the current, and that will detect the phase of the
Electric field. Yeah. Simple concept in antennas, field is proportional to current. If I double the current, I'm going to double the field. If I add a phase to the current, I'm adding a phase to the field. Okay? Really simple. There are a whole bunch of proportionality constants we don't need to worry about. If I choose a patch antenna instead of a horn antenna, that constant is different. We don't care. Okay? Concept is phase. Okay? Now, how does this feature into the whole IRS system? Now, there was a question over here that how do I know where the user is? How do I know where to tilt the direction? So you notice this yellow line, dotted line between the base station and the IRS. This is some kind of a control channel which is going to figure out where the user is. Okay. Now there are some technologies that are there which allows you to figure out where an unknown radiation is coming from. Okay. You have that, for example, in if you have an array of microphones. You know, there are things called direction of arrival algorithms. They will figure out where is the source of energy coming from, right? So if these users over here, they're also always transmitting a pilot signal. I am here, I am here, I am here. So this IRS over here, if it is equipped with a direction of arrival algorithm, it can figure out, okay, this user is here. Let me change my beams accordingly. Question? They are not, nothing is physically connected. Is also wireless. Right. Yeah.
I'm doubting that all the IRS will not be having a control mechanism with the base station.
Okay, so question is, will IRS and base station always be in line of sight? Essentially. We are assuming that to be the case. Let us solve that problem before we go to even more complicated problems. So let's assume that base station and IRS will be in. There are some algorithms that we have seen where there is no coordination needed between the base station and IRS. The IRS works in an automated way. That's also possible. I just need to know where the user is, right? But the reason why I need communication with the base station is because the base station, let us say there are users A and B, it's sending some data for A and some data for B. How do I know which is A and which is B? That's why some communication is needed between the base station and this IRS to figure out where to send which data.
Say there are 3 to 4 users at a time they have to receive the call.
Correct.
So, I mean, at those 3 to 4 users, the amount of base error should be different.
Different.
How is that?
So that is also possible. It's a very good question. So what he's saying is, I have drawn just 2 users. What if there are n users? Each of them needs their own beam. Each of them therefore needs their own phases. So typically what happens, for example, even on your current phone, everyone gets a slightly different frequency. Your phone and his phone are connecting to the base station at slightly different frequency. So that is what I will do. And I mean, it gets more and more complicated. The more functionality you want, the more complicated it gets. So at one frequency, there is one phase shift. At another frequency, there is another phase shift, right? So this is sounds difficult. From the other point, this is like an engineering goldmine. There are so many interesting problems to be solved over here, right? So how does this work? Each of these little green boxes, it imparts a particular phase. Now, when I do a linear superposition of the waves from all of these guys, like in the antenna array example, I can make them constructively interfere here but not here. So I have achieved my beam tilting. That's the basic idea over here. Details are of course very, very complicated, right? So
How is the phase added at the point of?
I will talk about, so how he's asking how is the phase added. I said by magic, but as we go further, I'm going to talk about how this phase is going to get added. Okay.
The IRS can cater limited number of users.
The IRS will be limited to, it can cater to a limited number of users. The more complicated engineering you do, the more users you can take. Now the thing is, this IRS is going to service a small area, so it may not have. No, it's not just a passive reflecting surface, and you may have lots of these surfaces if you have lots of users. In fact, if you have lots and lots of users, it may be more economic to put a relay. So these are economic questions. Okay. So finally, the question which he was asking, that how do I impart this phase, right? So what are the three main components that an IRS is made of? This is really, now we are getting into the nuts and bolts of it. It has something which is much, much smaller than the wavelength, okay? It needs something much, much smaller than the wavelength. I'm going to call it a unit cell. So I'm going to make this IRS out of tiny unit cells whose main feature is that they are much smaller than the wavelength, and why that needs to be also I will explain to you. I'm going to repeat this infinitely in space, okay? And the third thing that I want from it is that it should show an electromagnetic resonance. Again, I'll explain why that is necessary. So these are sort of the three main ingredients of the dish that I'm making, okay? When I do all of this together, this is what is called a meta surface, okay? If you repeat it in 3 dimensions, it's called a meta material. Okay, the word meta means that it behaves as though it is an artificial material, but it's actually not. You could make a meta surface or a meta material out of glass and copper, and it will behave as though it is some exotic material. That's why the word meta. Okay, this is what it can look like, a meta surface. So these are small copper rings that are arrayed infinitely in 2D. Has anyone heard of invisibility cloaks? Harry Potter, right? Has anyone made them in real life?
There was some article I read a few years back about someone about how he passed away and you could penetrate through them or something like that.
Correct. So the so-called invisibility cloaks have been made a few years ago. They are not like Harry Potter cloaks, obviously. They will work at one frequency or a small band of frequencies. So in other frequencies, it's not a cloak. So the idea which they used was actually use of metamaterials and meta surfaces. The core essential idea is that when I play around with the dimensions, again, it's in my hand. I can design it to be what I want. I alter the effective refractive index that the wave sees. I can in fact make a negative refractive index material also. So if I have a negative refractive index, your laws of refraction and reflection, Snell's laws, they will predict all sorts of funny things, right? So instead of going and reflecting from the object, the rays curve around the object. So the user, at the other end, doesn't see anything inside over here. That was the concept used in the invisibility cloak, right? Again, lot of uses in military applications, which is why you will not get to read too many details. Some papers, famous papers are there in the last 10 years which have shown this. So we are borrowing that concept over here for our use. Why? Because we want to do something much simpler than an invisibility cloak. We just say we want to bend light according to what we want. Okay, that's the idea. Yeah. IRS locations will be fixed. Pardon me? Okay. Correct. No, that's what I was talking about earlier. Why to do all of this headache if you can just put another antenna over there, right? So that another antenna is going to be called a relay. It has to get the information from the base station and retransmit it. It's like a mini base station, right? That is expensive. So if I wanted a cheaper solution, this is a cheaper solution. So what you're saying is the first thing to do. Put another relay station. But it's expensive, so we are asking, is there a cheaper way of doing it? This is the thing.
Other than the control receiver, these are passive relations.
We'll come to it. I'll come to it. Okay. So this is roughly what a meta surface looks like, right? Now this is a sample drawing of a unit cell, right? So here there were rings over here. This is also like a horseshoe, right? This is a horseshoe, and I'm showing you only one unit cell. This is going to repeat infinitely in X and Y and make my metasurface. Now to introduce the idea of a control, at the center of this guy, I'm going to imagine I'm going to put a diode or a variable capacitor or something like that. Okay, that's going to be my meta cell. Alright, so that's where it's not purely a passive device. I'm going to put some diode. If I put a diode, it's going to have a biasing network. So it's going to take some power. Okay, why we need to do that, I will come to. Okay, now what happens if I do a straightforward electromagnetic simulation of this guy? So what do? I send it a wave and I look at the reflection. Simple enough thing. When I do that, I observe something very strange. Remember, the third point of the metasurface was it should have a resonance. Now, why should it have a resonance? The blue curve over here is the amplitude. This is the reflection amplitude. The red curve over here on the right y-axis is the phase of reflection. The resonant frequency is somewhere next to 24 point something gigahertz. So, if I want, what are the main things I want to get from this graph? If I were much less in frequency, if I were, let's say, at 22 gigahertz, 21 gigahertz and so on, the reflection phase looks to be how much? About 330 degrees. And if you draw this curve further, this red line sort of flattens. It just becomes flat. So less than 24 gigahertz, the reflection phase is always 330 degrees. Nothing else is happening there. Once I go past this resonance frequency all the way over here, you'll notice this red curve flattens over here. Where is it flattening? This is roughly minus 30 degrees, thereabouts, right? So what the resonance is doing, it's allowing me to swing the phase from theta to theta plus 2 pi. This is roughly 360 degrees phase swing over here. So that is what is the main quality of a resonance. And I mean, again, this is not something very exotic. Water has resonances in the optical frequency range, which is why you are able to see a rainbow, right? If I talk about this in terms of refractive index, different colors see different refractive index, which is why a rainbow splits light or bends light, right? That same concept now we are using at gigahertz frequency. So the presence of a resonance is extremely important. If there were no molecular resonance in water at optical frequencies, you would never see a rainbow. It's as simple as that. Okay, so this resonance is a very key point. That's why the design of this metasurface, it's very important that I get this resonance roughly where I want. I shouldn't get too close to it, because what will happen if I get too close to the resonance? Look at the amplitude, right? The reflection amplitude has gone below 0.1. So it's effectively I send energy there, nothing comes back. Reflection coefficient is close to 0. So this is kind of a trade-off. I want to be close to the resonance but not too close to the resonance. So this is basic concept of a static meta surface built of one unit cell. So if I build all of these guys, at any given frequency, I'm going to see only one phase. It's either going to be here, any point on this red line. So I have not achieved this dynamic operation so far. Yeah. Yeah. No, so okay, we have to be a little careful over here. Supposing I put an object over here which completely absorbs light. So when I look at it, what will it appear to be? Black. There's no cloaking. Cloaking means it should go around it. I shouldn't see anything different from the background. So I don't want to operate at this frequency for cloaking also. We'll talk about it. I mean, it's a totally different application over there, right? So what I showed you here was one type of resonance, right? There are people in the literature, they have made all sorts of fancy unit cells. So here is, it's called a split ring resonator. It's a C shape with something over here. Now what is the, they look really funny, but they're actually very simple to understand. When I put two pieces of metal close to each other, what is it acting like? Capacitor, right? That explains these two rods over here. When I have some length of wire, what does it look like? Apart from a resistance, it's like an inductance, right? So this is like a LC circuit with some resistance here because copper has loss, right? So this is here. If you put two things over here, you get two capacitors, two inductors, right? So this is your design canvas you can change the dimensions over here, you can change the length over here. You need not be restricted to square geometries. You can go crazy with all sorts of shapes. Here are 3 slots, 4 slots, so you can make it more and more complicated, so that you know that what is the property of a LC circuit? It has a resonance frequency 1 by root LC. So I can change the resonance frequencies to be what I want depending on whatever the 6G guys decided, right? So now how small should the unit cell have to be? This is a very important question. How small should it be? Should I make it 1 wavelength, half a wavelength, 1/10 of a wavelength? We don't know this. So this slide is probably the only slightly technical slide. So I'll go through it at a little faster pace. So here is a wave that is coming from the bottom. Think of a glass slab. If I send a wave, it's going to hit the glass slab. Some energy will get transmitted, some energy will get reflected. That's the same thing that's happening here, except that this is not a glass slab. This is a glass slab in which I've put some copper slabs in a periodic fashion. So think of copper wires, I've put them in a periodic fashion. When I put them in a periodic fashion, it's what is called a grating. As a result of this grating, instead of having one reflected and one transmitted wave, I get a series of waves. Okay, this is physics, you can work it out. You get a series of waves. Okay, this is just fact. Then what is the next step? If this slab were just homogeneous, if it were a piece of glass, I'll get one reflection, one transmission, no problem. Now, when I put this grating over here, my metacell looked a little bit like that. It had some pieces of copper, then it had some nothing, right? So my metacell is a little bit like this. I don't want the beam coming from the base station to get split into so many modes, because the user is in one place. So I don't want this to happen. So in other words, I want to retain only one mode, which is the m equal to 0 mode. How do I do that? It turns out that if the length is less than a quarter of the wavelength, then all the other modes die out, approximately. So this is the sort of key ingredient which tells us how big should the unit cell be. If I make the unit cell too big, my incident energy is going to get split into so many different things, which is not good, right? So that tells me, that's why the first point of my meta cell was sub wavelength. So this is telling me it has to be at less than quarter of a wavelength. The lesser the better. What is the problem with lesser the better? Making it is difficult, because now every dimension is really, really small. Okay. Let's come to the interesting part. I've done all of this. Now, how do I actually steer the beam? We have not spoken about that. For a single unit cell, this was the response, right? Now, I obviously cannot have infinite unit cells. So I have to truncate it somewhere. So let us say I keep 20 units, okay? So one green box over here is consisting of, let's say, 20 by 20 unit cells. It's a good approximation to an infinite summation, okay? And each of these green boxes sends a different phase, okay? So imagine I have different designs of metasurfaces on each green box. So the phase that each one of them reflects is going to be different. So this is like the phased array idea. Each point is giving a different phase, and they will give a constructive interference in different directions. If I can control what phase they give, I'm back in business, right? So let's now boil down to how to steer this beam, okay? Now I need to therefore introduce some kind of a control. So remember that this was the circuit equivalent of my unit cell. It's a LC circuit, right? Supposing I insert a small impedance into this. You've all heard of variable capacitors, where if I change the supply voltage, the capacitance changes, right? So there's a varactor diode, it's called, or a pin diode. All of these things, what they do is they alter the circuit equivalent of this. If I change the circuit equivalent, what will happen? The resonance will shift, right? Now when it shifts, so this is a practical demonstration. I have a substrate, this is a dielectric material. You've seen your PCB boards, right? And your TV or laptop, that green color thing. So it's that green color thing. And some copper is put on top, and I put a diode over here. So when the diode is on, there is some capacitance. When the diode is off, there is another capacitance, right? So I get two different resonances, right? This is the main part of it. So with one resonance, I get the dashed curve. With the second resonance, I get the solid curve. So notice that the resonance has actually changed in frequency. The first resonance was here at 24 point something gigahertz. The next resonance has gone to almost 25 point something gigahertz. So you might say, so what? The actual mystery is resolved not in the amplitude, but look at the phase. If you look at the phase, the red lines, the phase response is different. So if I pick a particular frequency, let us say I pick this black line over here, phase is P1, phase is P2. There is a phase difference between these two. And I can make this phase difference to be, let us say, 180 degrees or whatever I want. So that means that when the diode is in state 1, the reflection phase is 0 degrees. When the diode is in another state, the reflection phase is different by 180 degrees. Right? So I can achieve a control because I can change the biasing voltage of the diode electronically. I don't have to do anything. I can have a full biasing network, let's say 2 volts or 4 volts. When it is 2 volts, the phase is P1. When it is 4 volts, the phase is P2. Right? So this is how I achieve the dynamic control. Okay? Yeah. Yeah. Correct. So he's raised the devil question, right? Notice what happened to the dotted blue line. The amplitude is dying. That means, as I said earlier, I want to stay away from this line. So supposing I choose to operate my IRS at 25.5 gigahertz. Look at the amplitude. How is the amplitude doing? Not too bad, 0.6, right? And the phase difference is now Q2 minus Q1. Not as much as earlier, but I've got something. So in this field, this is the whole ball game. Keep the amplitude as high as possible, but get a phase swing between the two states. If I get a phase swing, then I can use it to steer a beam, because this green tile has so much phase, that green tile has so much phase, I can change the direction. Okay. So we call this a 1-bit metasurface. 1 bit, why? Because there's only 1 bit of control, on or off, right? So there's a lot of complexity here. How do you design the biasing circuit and network, right? Space limitations, right? A diode takes a certain amount of space. I already told you lambda by 4. So supposing I'm designing this at 10 gigahertz. At 10 gigahertz, what's the wavelength? 3 centimeters, 30 millimeters. Lambda by 4 is 7.5 millimeters. That means the unit cell has to be minimum 7.5 millimeters. Let us say I make it 5 millimeters. What is the size of a capacitor? Right? All of these diodes, they need a capacitor, they need various things. Right? Now I need to start hunting for pieces of lumped elements which are like 1 millimeter, 2 millimeter in size. So it's going to get more and more difficult. If I start increasing from 10 gigahertz, if I go to 30 gigahertz, good luck, right? So this is why it's challenging. That's why when people say 140 gigahertz, I really scratch my head that, it's going to be, there are no lumped elements then. We'll be fabricating RF ICs instead, right? Which is actually part of the research which our department has signed up to do, which is to build RF integrated circuits to do all of this magic at 140 gigahertz, because there is no diode and capacitor available. You have to make this in the integrated circuit, right? So tremendous research opportunities are there. Okay, right? How do I design this such that I get the best amplitude and best phase response? This is not electromagnetics, this is numerical optimization. This is machine learning or data science or whatever. How do I, because these electromagnetic simulations, it looks very nice for me to show you this one graph. These simulations take a lot of time. So I need to work with expensive simulations and optimize structures, right? So these are in summary the key points of this IRS, right? We have what is the main problem that it solved? Coverage. Where a direct line of sight was not available, I put this IRS, it gave a reflection path, I solved the coverage problem. I did not need to decode the waveform. That's great in terms of cost. There's another interesting use of this IRS, which recently people like, I think, Tata Telecom or Jio, they got in touch with us saying, we have heard of IRS, we've heard that you're using it for 6G, but we want to use it for 5G. In a situation where the users have direct line of sight, So can you imagine why would anyone want to do that? There is line of sight, still I want to put a IRS. Bandwidth is the same. There is more diversity, there is more channel capacity available. So people did simulation studies, you could increase the capacity by 20-40%. That means I can give better quality of service to the existing users. So you will see IRS deployed even before 6G comes out for 5G applications in very dense urban places for increasing the capacity. Okay, there are like hundreds of papers being written on this, like calculating what is the capacity. So this is, probability, wireless communication statistics, all of that stuff. Not necessarily, they don't even know electromagnetics and they don't need to know electromagnetics, right? So there's really a very, very diverse field of things, right? Now, what all do we need to understand? We said the frequency of operation, as I said, it's up in the air, right? The unit cell design is up for challenge, right? How do we solve it? Do we use traditional optimization? Do we use AI ML? This is all up in the air, right? How many bits should we use for beam steering? The example I gave you, I used only 1 bit. There are people who have done 2 bits, 4 bits. That means I am putting those many diodes in each unit cell and I have a control circuitry for that. So instead of 0 and 180 degrees, I have 0, 90, 180, 270. Now I can have a finer control of the beam. So no one says that you can only put 1 bit, you can put multiple bits, right? But then have fun with the bias, the circuit design, right? How do I figure out the feedback between the IRS and the base station? These are again things that have to be decided at the protocol level, right? This is not EM, right? And of course, channel studies. How much better does the communication channel become once I add a IRS, even when there is line of sight, right? These are all very, very rich problems. So I've about at 1 hour, next 5 minutes I'll wrap up. The main meat of the talk in terms of technical content is over. I'm going to talk about one application of increasing the data rate. One was going to higher frequencies, second was full duplex. The third is exotic electromagnetic states, which are called orbital angular momentum. Now, orbital angular momentum has been known in the field of optics for decades. Not surprisingly, there was some Russian who discovered it, okay? And what we are used to when we think of an electromagnetic plane wave is this, where the phase, which is the left column over here, is constant. In a plane wave, the phase is constant in the entire plane and the amplitude may be like a Gaussian, right? A realistic plane wave will not have the same amplitude forever and ever, it will die out. That's our wave that we know. In an orbital angular momentum wave, the electric field vector doesn't stay in the same plane. It goes like a helical path. It rotates like that. And how fast it rotates is called its orbital angular momentum. So this is called a +1 state. A +2 state is it rotates twice as fast within a wavelength. So you notice over here the phase is going from 0 to 2 pi. Here the phase is going from 0 to 2 pi to 4 pi. So the number of times it changes the phase is its quantized angular momentum. Okay. So these come out as approximate solutions to Maxwell's equations, and each of these modes, like I said earlier, in the case of TM polarization, TE polarization, they are all orthogonal to each other, which means they don't talk to each other. If they don't talk to each other, I can put separate data on each of them, right? So if I had a problem of data rate, I'll just put different pieces of data on different modes and they will all travel together parallelly, there's no problem. That's how you can increase the data rate. Okay. How do we make them? Traditionally in the optics world, what people will do, they will use things like spiral phase plate. It's a really low tech thing. You make a piece of glass, but you shape its vertical dimension like a spiral staircase, right? Made out of glass. So as the wave goes through it, each point on the wavefront gets a different amount of travel through the glass. So its phase has changed. It ends up being an OAM mode. Nothing very fancy about it. This is what optics people do. Or they use these holograms, right? Optics people are here. These holograms will, and they will know much more than me, can be used to take a simple Gaussian mode and split it into different OAM modes. So there's a lot of again, engineering challenges of how do you design these things. This is in the optics world, but we want to do this in the RF world, right? So I'm going to give you two high-level ideas, and then we'll end the talk. The first idea is actually very simple. Here is our unit cell. Remember a metasurface? A very much simpler unit cell, just a piece of copper, red copper, right? Now what people did is, if I just change the dimension of the copper, over here this graph, the x-axis is the size of the copper patch. As I make the copper patch bigger or smaller, the reflection phase changes, right? If the reflection phase changes, what I do is I have an input beam, and each of these red things over here has a different size. If it has a different size, it's going to reflect a different phase. So I can construct whatever phase pattern I want. I wanted to do 2 pi, I wanted to do 4 pi, I can do all of that over here. So you can see input feed is a plane wave, out is coming beam 1 and beam k and so on. This is possible.
But that will be fixed.
This will be fixed, right? This is going to be, unless I put a diode in each one of these characters, right? He's already doing this. But if you want a dynamic metasurface, that's what you'll have to do, right? So these are a few of the tricks of the trade. Put in a few RF switches, diodes, whatever. You can make the beam do all sorts of things you want, right? Now the final example is a really cutting edge example from NTT Japan, right? So when NTT Japan does something, you better take notice. What they did is they said we are not going to use metasurfaces. They used a concept of antenna arrays, which I already told you about, but I put it in a circle instead of in a rectangular array. So there are, for example, you see a 1, 2, 3, 4, 4 uniform circular arrays. Each of these dots is giving a certain phase. So in one circle, I can have 0, 90, 180, 270, back to 0. So the wave that is generated out of these little dots, each of these little dots is a small antenna. It's going to mimic a phase of what I want, right? So that's what they did. This is the actual device that they made. They used a combination of OAM modes and polarizations. I was calling them TETM. In their literature, they call it horizontal and vertical. Same concept. They combined this and this to deliver 200 gigabytes per second over 10 meters at 28 gigahertz. So prior to this result, and this is actually their setup over here, prior to this result, I don't think there was anyone who had demonstrated such a high data rate at gigahertz. Such high data rates are even, I mean, if you tell optics people, they'll be very happy if you're, what would you say? Is 200 Gbps very easy in the optical? Very good rate, right? Very low, right? So that's what makes it very impressive, right? And so this is possible. So it's not always metasurfaces, but circular arrays also do it for you. And which one to take, we all will decide in the next 5-10 years which is the way to go, right? It's all up for design. So how did they get such a high data rate? Each circular array was doing multiple OAM modes, multiple polarizations, multiple modulation formats. So if you read their paper, which is linked over here, it's very, very complicated. We still can't figure out exactly what they did. They have not even mentioned all their details, intentionally so. So, no, each array carries different sets of data. That's how you're able to multiplex and get such a high data rate. Okay, it's a 4-page paper. That's all. I mean, if they were in academia, they would have written a 20-page Nature paper about it. But they are not. Their bottom line is more important, right? So, okay, in summary, you had a question? No, okay. We've looked at, I mean, this is absolutely fundamental, right? What is the role of carrier frequency? It influences data rate, it influences coverage in opposite ways. So, we found out that to get over the coverage problem, we need these reconfigurable intelligent surfaces. Why are they called intelligent? Simply because they can dynamically change their phase depending on where the user is. That's all that there is no ML happening over here. Okay, it's intelligent in that sense. You could have instead called it adaptive reflective surface or dynamic reflective surface, but the fashion of the world today is to call everything intelligent. Your fridge is also intelligent, right? When we looked at metasurfaces for implementing the IRS, right? And I gave you a very brief overview of orbital angular momentum. And question, huh?
In that method only phase difference
Correct.
between two rays.
Correct.
The gamma also affected, right?
You mean the amplitude? We want to keep that as high as possible so that I don't lose energy. So that's a design criteria. Give me the phase difference, but amplitude should be as high as possible. Otherwise, I have lost the signal.
Maybe bit nuanced question. Like generally, how we do transmission is we have constellation.
Correct.
Data constellation,
Correct.
I and Q.
Huh.
We send one on cos, one on sin.
Correct.
That's we do. With OAM, you are saying that
All of that is still true.
no, we have four OAMs,
Huh.
and then maybe two the H and B.
Huh.
So we can send 6 data streams for the same frequency. That's
Correct.
How do we do the modulation of the, like how do
So these guys which I am showing over here, they did a very strange combination. The center element was sending 256 QAM, one array was sending 64 QAM, another was sending 64 QAM. How they distributed the data between this has not been revealed. Okay, so it's something for us to work out.
what is input to these? So there are like 4 arrays, right?
There are 4 arrays and a center element.
And so 5. So voltage input to these, that's the analog waveform.
Right, right.
They are different.
They are different.
So I have 5 different waveforms.
You have a lot of elements in between your signal generator and here, which is, I mean, you should read the paper for it. It's quite complicated. There's something called a Butler matrix they use and so on, but let's not go into that. Okay. And I mean that's about it. So I hope I've been able to convince you that it's a very exciting research area. It's very interdisciplinary. Yeah, question.
Sir, the point of IRS was to avoid obstacles.
Correct.
Why not work with something satellite communication?
Why not work with satellite communication? Well, with satellite already the huge problem is that it's at such a distance that your power, everything will be so power intensive first. Second is if you're inside a shopping mall, you don't even get your GPS, right? The signal doesn't come when you're indoors. So your satellite will not help you once you're indoors. So that's why satellite is, and it's hard to put high bandwidth also on satellite. So satellite is good, for example, for broadcast, right? The same information going to everyone is great. But I have like 60 people in this room, each one watching a different YouTube video, right? It's not the same information. So the amount of data rate required increases, right? So one possible use case I have heard of this 140 gigahertz is, for example, when there are, let's say, a few lakh people in a stadium watching IPL. Now, so many users concentrated in one place, I don't have a big enough data pipe to send them information. So there is where this 140 gigahertz, 270 gigahertz, you may have dedicated such things in these stadiums and shopping malls so that you can service all of these people. Right.
I'd like to check on your assertion about IRS increasing capacity. I guess it increases diversity for sure. They add
More paths, yeah.
So it's not like a new antenna, right? So it doesn't give you more degrees. Well, it doesn't give you multiplexing.
It doesn't give multiplexing.
It's not like
It's not multiplexing. Yeah, it's there is more spatial diversity is what is giving the improvement.
I guess then you get more better, probably better.
Correct.
But not more capacity.
Yeah, that's. I'm sure you're right.
No, your dependence on the probability of error on the SNR will be better.
Will be better.
Yeah, it doesn't give you multiplexing data.
Doubt from the IRS part. So when you change the phase to one direction, the other input wavefront also changes, right?
No, what we are changing is the reflection phase. So the input, let us say, is coming from the base station. That is coming with its particular phase front. The reverse, yeah, it's reciprocal, right? So if I do it in this way, the same thing will work when the user transmits. Now it will go to exactly to the base station. It's a reciprocal device. I mean, that's very crucial. It has so happened that it is reciprocal. Otherwise, then when the user speaks, it will not go to the base station. That's a problem. But that's a good question. Yeah.
How do you know whether you
How do you know where the user is? So part of this is the protocol. So the user may, for example, if you look at the way people do OFDM and all of these, there are certain periods of time where the user just sends a pilot signal. And you are looking for a user in that period of time. The first 10 microseconds, the first 20 microseconds, they just send like a tone, a sine omega t. So on the IRS, as I mentioned, this direction of arrival algorithms, they can figure out from this entire space where is the user, right? So that is a piece of technology which helps figure out where is the user, which is done like directional mics you've heard of, or directional, right? When you have a conference room and you want to isolate the audio from one person. All these James Bond movies you've seen, right? It's a directional mic that goes and picks up audio only from one point. It's not exactly science fiction. It's this constructive interference in one direction. In the reverse mode, it becomes like direction of arrival. It will be a finite surface area. Yeah.
Assume an incoming wave is coming. The IRS is reflecting at theta 1.
Right.
And the remaining area surrounding the IRS will be reflecting theta 2.
Correct.
So both waves will be present at the receiver point.
With different reflection coefficient. So if my building has a poor reflection coefficient, it will not reflect so much. I have to take care of all of that.
Because both are at same frequency.
Right. Yeah. So stray reflections have to be taken care of.
And the power, what is the minimum surface you require for this?
That's a calculation that you have to do. It's called link budget analysis. How much power is required, you can do that calculation. Not a very difficult calculation.
This IRS technology, it's dynamic and adaptive because the users could be moving in this space.
Correct.
So can this be used for high mobility applications?
Yeah.
Can the adaptive?
You need it when you are going out of line of sight. But if I am in line of sight, then I don't need. But if I am going in and out of line of sight, then yes, I need this.
No. By high mobility, I mean let's say the user is moving in a train.
Correct. So okay, what happens when the user is moving in a train? So there are two ways of doing it. If the base station is on the ground, then the base station has to track this user. The smarter thing may be to put a repeater or something inside the train, and that train just needs to connect once to the. That's possible. So those of you who need to leave for your dinner, please feel free to head out. Correct, on the train, and that could be at a higher frequency.
So we are assuming the RIS speaks to the base station.
To some extent, it's not possible for there to be no communication, but some kind of a wireless link of sending some, because the
base station speaking to RIS is one.
Okay.
I'm talking about RIS speaking to the base station.
Yeah.
I thought
That need not be actually. That need not be.
But then, if there is no LOS, the base station doesn't know where the user is. It's the job of the RIS to tell where the user is.
It will all depend scenario to scenario. There are various possible scenarios and people are working out all the details. So, if I make some statement, we can contradict it in another scenario. So, those are we want to stay at a little higher level over here. Any students currently doing engineering electromagnetics? Okay. Could you follow most of it? Okay, good. All right. Thank you so much. Thank you.